Hi, I'm glad that you're about to watch my overview of a design course that I developed for the University of Florida. Instead of having the students build model airplanes, I wanted them to develop the computer skills so important when they join industry by designing and testing a UAV solely on their laptops. Now, this seminar was originally given as an online webinar under the sponsorship of the American Institute of Aeronautics and Astronautics, but now I will give it as a service of my company, Modeling and Simulation Technologies. Since we don't build hardware, we call our approach conceptual design, meaning that we'll have several solutions to meet the requirements using our limited assets, which is just our personal computers. But we will make use of quite a few of these aerospace disciplines like aerodynamics, propulsion, equations of motions, well, even guidance and control. So through mathematical modeling, we do that in our workshop and we use our simulation as the flight testing. And that will give us an opportunity to use theory to design using our computer skills. Now in this video, I'm just giving you a brief overview over this course, how to design, or I should say conceptualize a UAV, and then build a simulation which we use to test our design. I will discuss some of the benefits of computer-based conceptual design and wrap it up with some additional resources that you can use to develop your own project. So let's get started. Here is a bird's eye view of the University of Florida Graduate Center, which is actually called the Research, Engineering, and Education Facility, in short, REEF. You can get their master's and a PhD degree in some of these focus areas, particularly autonomous flight, mission control laboratory, or precision guidance. I taught there over 35 years of graduate courses in flight mechanics, guidance and control, INS, and particularly focused on modeling and simulation. Now we may have team projects or collaborative research projects. I would provide tutorials in areas and then short courses, again focusing mostly on modeling and simulation. Now a typical system design course may require the students to have background in aerospace design, flight dynamics, automatic control using MATLAB, and the C++ programming language. We would have 2 lectures reviewing prerequisites, particularly with emphasis on mathematical modeling of these aerospace disciplines. Then there may be 2 computer lab credit hours with overview over the design codes and the missile simulation, and then lots of questions and answers. And a design team may consist of 2 or 4 students. They would bring their laptops with a C++ compiler, TurboCAD, MATLAB, and DATCOM, load it all up, and go through 3 phases: project definition, project execution, and then final presentation, which was usually competitive, and the winner would get a trophy. Now I'm going to show you 2 projects, a missile project and the UAV project. Of course, we're going to concentrate here in this seminar on the UAV project, but let's start with this missile project. First, I may give the requirements what the aircraft constraints are, the launch envelope of the aircraft, the terminal accuracy requirements on the UAV, and then a test profile which will prove the performance of this particular design. And the design is done in TurboCAD as layout. The aerodynamic tables gotten from missile.com, rocket propulsion from my book, and controlling guidance also from my book with use of MATLAB. I would provide to them a 6-stop simulation that they then modify for their particular design in order to verify the launch envelope accuracy and flight profile, and then generate briefing charts for the final presentation. And here is a reference of my book in 3rd edition at AIAA. Now, this is the project we're going to concentrate in this particular seminar. I would give requirements in terms of payload, cruise range, speed, altitude, and again a test profile. They would use TurboCAD for layout. In this case, generate aerodynamic drag polars using the aircraft.com, propulsion again from my book, as well as control and guidance with MATLAB usage again. In this case, I would provide them with a 5-stop simulation that they modify to verify performance and the flight profile. And then they produce the final report with briefing charts. And here is the aircraft.com reference, and again my book in its 3rd edition. Now, in an online webinar, which is live, I ask these questions and you can answer them, and we would tabulate them and show everybody what your opinion is. Here, since it is offline, I just ask you these questions, and you may share them with me by email or not. So UAV acronym has 3 different types of interpretations: unmanned, uninhabited, uncrewed, or we may use UAS, unmanned aircraft systems, RPV, ACV, air combat vehicles, and very popular are drones these days, embracing all these various aspects. Now, you may have your own secret acronym. If you do, well, keep it secret or share it with me by sending me an email. The first step the students take is designing the airframe. They determine the outer dimensions, which are called the mode lines, and then decide on the kind of material they're going to be using, which leads to the determination of the mass properties. The aerodynamics are obtained from DATCOM, and they select a turbojet and the data they get from the suppliers. Now, I will use a particular example to show you what typically the students go through as they work on this project. Here is a typical example of a UAV. Its length is 5 meters and its span is 2.8 meters. You would get this using TurboCAD, and then you have to decide on materials and structures, and that's usually done based on historical data. The mass properties you also can get from TurboCAD, or you can do some hand calculations. Then you determine an airfoil based on a NACA selection. And with this, you can calculate the aerodynamics using DATCOM. Now, Gundlach is a pretty good reference to get some of the information on how to design unmanned aircraft. So we have here these mass properties. The launch mass 1,000 kilograms. The max fuel mass is determined by the range requirements, as well as the payload are given by the requirements. Now we are using a simplified aerodynamic representation of this UAV using drag polars. That's quite adequate and useful for 5 degrees of freedom simulations. As you see, drag coefficient is plotted against lift coefficient, and as the Mach number increases, the drag increases. We also need the lift slope curves. Here we plot lift coefficient versus angle of attack, and as you see, they are linear, and the slope is almost constant throughout the Mach range. We select as propulsion a turbojet. This is a radial turbojet. The sizing of the turbojet engine is based on the thrust requirement, which in our case, since we do mostly cruising, is cruise drag plus a margin. The performance data you need to get from the manufacturer, and the fuel mass is given by the range requirement, as I stated earlier. To build a simulation, we need a propulsion deck. Thrust available is a function of Mach number, altitude, idle thrust also, and then we need to calculate the fuel flow to keep track of how much fuel is left, and that's a function of Mach number, altitude, and thrust. And also we need the idle fuel flow. So here is an example. Let's say we cruise at Mach 0.7 at an altitude of 1524 meters. Then the thrust available is about maybe 1900 newtons. To get the fuel flow, we go into several tables. As you see, they are given for different altitudes. In our case, since we are flying at 1524 meters, we use the middle table. We cruise at 0.7 Mach, and the thrust we need here to maintain that cruise is 1446 Newton. So we go into this table at 0.7 Mach and the thrust, and then we see that our fuel flow in kilograms per second is about 0.04. In order to cruise at a constant Mach number, we need a Mach hold controller. Well, we have a Mach number required, let's say 0.7. That is required compared with the actual Mach number measured. It goes through a gain, GM. Then we add to it the thrust required based on the drag at that particular Mach number. Then it goes through a lag, which represents the spool up and spool down of the turbojet. And finally, it is limited to not exceed the max thrust required, or the idle, and out goes the thrust itself. Well, here we are again, polling questions. And as I mentioned earlier, in the live presentation I made, I asked the students to give me some feedback. But here you can actually query yourself what your favorite discipline is. Structures, aerodynamic, propulsion, autopilot, navigation and guidance, seekers and sensors. But as a design engineer, you really should be cognizant or capable of dealing with all these particular aerospace disciplines. After the students has designed this UAV, with its mold lines, mass properties, aerodynamics, propulsion. Now he has turned to control and guide it. He will be able to choose from 6 autopilot options and 2 guidance options. And I will show you now what those options are. The autopilot steers the airframe based on a command which is compared by the feedback that's generated from sensors that sense the airframe modes. There are 8 particular modes the students can pick from, which are provided by my book. Bank angle control, flight path angle control, heading control, normal and lateral acceleration control, and altitude control. He will use MATLAB or Scilab to design the autopilot using methodologies like pole placement techniques or the root locus methodology. So let's look at some of these autopilot options. Here we have bank angle of control. The command comes in from the left side, is limited, and then sent through a lag, which represents the inertial lag of the autopilot to turn the UAV, and out goes the bank angle. Then we have the flight path control. The difference between the commanded flight path angle and the measured flight path angle is sent into a gain that converts it into an acceleration. The banking of the UAV is compensated, and that acceleration is converted into an angle of attack limited, and that angle of attack then drives the dynamics of the UAV. In heading control, the commanded heading control is compared with the measured heading, sent through a gain to convert it to a bank angle, which is sent through the bank angle control. And then this bank angle enters the force module and the vehicle dynamics to achieve the required heading. In the case of altitude control, we are comparing the commanded altitude to the measured altitude sent through a gain, and now it's compared with the altitude rate sent again into a gain. The gravity bias is introduced, and this is again compensated by the banking of the UAV, and this acceleration is entering the load factor controller that in turn changes and controls the angle of attack. UAV guidance is particularly dominated by waypoint guidance because this will shape the trajectory of the UAV as the UAV flies through various waypoints. The equation here shows that the sign of the bank angle command is a function of the velocity squared of the UAV divided by the range to go, the normal acceleration, and g being the gravity constant, times the sine of the heading angle. You can find some of these terms on the left side. B is the position of the UAV, W is the waypoint, and you see here the heading angle and the range to go. As the UAV has to approach the runway and land, there is a terminal guidance requirement which generates acceleration commands. We have 2 line of sights. Well, one is the line of sight between UAV and the IP. The other one is a line of attack. And this line of attack aligns the UAV with the runway direction, both in the vertical and horizontal plane. So here the idea is to bring the line of sight into the line of attack for landing. You may be overwhelmed by these guidance and control options. And yes, guidance and control is not a simple subject. You may say, well, it's somebody else's problem. I will have somebody else do the GNC for me. And then there's the difference between classical control and modern control. Should I use classical or modern control? Well, it is very important nowadays to be an expert in both classical and modern control. Those that fly an airplane, maybe they say, "Hey, I don't trust my guidance and control. I rather use the stick to control my airplane." Yeah. Well, we'll see. A simulation is an integral part of any concept design. So I provide the students with my 5-step simulation, which is based on my CADAC framework, which they use to finalize the autopilot and the guidance, and then conduct a virtual fly-off, which is a competitive fly-off between the teams, write a final report, and make a final PowerPoint presentation. This UAV simulation is in C++, so the students must have some C++ background. It is a 5-degree of freedom simulation, which means that the UAV pitches and banks, but does not side-slip. So that is the missing degree of freedom. Its trajectory is tracked in longitude, latitude, altitude over a spherical rotating Earth. So we have true longitude and latitude. The aerodynamics, as I said, are trimmed aerodynamics, represented by a flight polar. Now, there are no real surfaces that are modeled, but the drag of the trimmed surfaces is included in the drag of the flight polar. You have seen the autopilot in its simplifications. The attitude dynamics are represented by transfer functions, so it's a linearized autopilot. Its output is angle of attack, which goes straight into the aero table lookup. This simulation is based on my CADAC framework. CADAC stands for Computer Aided Design of Aerospace Concepts. It is based in Microsoft Windows operating systems and is compiled by the Microsoft Visual Compilers. There's also a plotting option called CADAC Studio. You can do their 2- and 3-dimensional plotting, and I will give you some examples following here. You can also do plotting over the globe, and launch envelopes and footprints can be generated. So what is this UAV simulation used for? Well, the students will use it to optimize the controller gains in these 3 autopilots. Now, these autopilots may have been designed using MATLAB particularly to get the right gains, but this analysis would be just a linear analysis. Here in the simulation, the autopilot has to be validated with the nonlinear dynamics of the vehicle itself. It is also used to optimize the waypoint guidance, waypoint laydown, maneuver limits, and then we will also evaluate some of the key performance parameters: range, climb, and ceiling of the UAV. When all this is done, the fun begins with virtual flight testing and the fly-off competition. This is a quick view at the simulation. It consists of 3 parts. The core is this CADAC++ frame with its UAV coding. On the left side are the inputs. We got an aerodeck, a prop deck, and input file that initializes this run. On the right-hand side is the output in terms of plot files. Now, there are several plot files shown here, and that's the case if one take advantage of the simulation that multiple UAVs can be flown. In our case, we're just going to fly one UAV. All these plottings can be done in CADAC Studio. If you don't load up CADAC Studio, you also have another option, which is called the Computer Separated Variable option, which is very general and can be plotted with MATLAB and other these kind of plotting programs. On the bottom, we see here that there will be displays scrolling on the screen, and those can be archived in a tabout.asc file. Our UAV simulation consists of modules, which is a key of the simulation. It has a modular structure. Here are 7 modules. On the right-hand side, you see Newton's module, where the equations of motions are solved. It's driven by forces. Those forces are generated by propulsion and aerodynamics. On the bottom right, here is the environment, like atmosphere to get us density and pressure. We have a guidance module for Waypoint Guidance, and that drives the control module, which contains the autopilots, which in turn drives the aerodynamics. So let's look at some typical plots that the students would present in their final presentation. We first look at the flight path angle autopilot and want to determine the best gain. In the top frame, I've plotted versus time. This is a 30-second trace. I've plotted a command, gamma command in red, and then the response of gamma. You see the command is a pulse lasting for 10 seconds and a value of 5 degrees gamma. So let's look at that response and see what gain we would select. In order to get some more information, we also have to look at the bottom frame. Here I'm plotting angle of attack, which is very important here, the Mach number, and the thrust that is needed to maintain the Mach number. In this case, we are cruising at Mach 0.6. So the angle of attack really tells us a story. The gain 60 would saturate the angle of attack at 10 degrees. We don't like that. We rather would back off. Well, 30 just goes up there very briefly and then drops down. 15 doesn't require much, only about 6 degrees angle of attack. So again, combining both of these plots, looking at them, the student probably would select 30. And he would get an A for that. Let's look at the heading autopilot. The heading autopilot, as you may remember, is a bank-to-turn autopilot. So here we have a pulse of a 5-degree heading lasting for 10 seconds. And you see the responses. Well, 12 looks actually very good. 24 has some overshoot. 6 is too sluggish. But let's also look at the angle of attack. The 12 requires only about not quite 4 degrees angle of attack. That looks very promising, even though 24 would also be possible because it doesn't hit the limit of the angle of attack. But the student probably wants to be somewhat conservative and would probably pick 12 as the best gain. The altitude autopilot again is excited with a pulse of 10 meters lasting 10 seconds. Now this pulse is somewhat unusual. Usually when the UAV would change altitude, it would climb slowly, not with a pulse like this. But in order to investigate the autopilot, the pulses are quite useful. And we're looking at the traces, these green traces here with the three different gains. Well, 0.15 very sluggish, 0.3 we like, 0.6 somewhat too oscillatory. And that's also confirmed on the bottom here. Angle of attack really goes all the way up to almost 80 degrees. So again, the student probably would select 0.3. Now we switch to Waypoint Guidance, and there's a gain to be determined. What I'm showing you here is plotting latitude versus longitude. So that's like a ground plot. In the top frame, in the bottom frame, we're going to look at angle of attack and bank angle, also plotted against longitude. Well, there's waypoint 1, waypoint 2, and waypoint 3. There are three gains, 0.5, 0.6, 0.7. And looking at the angle of attack, well, 0.7 seems to drive the angle of attack quite high. Again, let's be somewhat conservative, and let's pick 0.6, which very nicely takes the UAV through all three waypoints. Now we will want to look at some performance, first at climb performance. The UAV climbs by commanding a gamma, which is the flight path angle. In the top frame, I've shown altitude, in red, Mach number, and the dynamic pressure, which is now becoming important. In the bottom, we have the flight path angle in degrees. See 5, 10, and 15. The associated angle of attack and thrust. So what is the climb performance? What's the maximum gamma that this UAV can climb with? The conclusion is 10 degrees, and that's driven by the bottom frame here, because you can see at a gamma command of 15, the UAV really can't maintain that. Initially it does, but then it drops down to even negative gamma. So what happening 15 degrees is just not achievable with this gamma autopilot. So we say yes, indeed, 10 degrees flight path angle is all that this UAV can accomplish. And there's another performance that's important, answering the question, well, how high can this UAV fly? And we're going to look at three different altitudes at a cruise Mach number of 0.6. In the top frame, you see in red the altitude, 7,000, 8,000, and 9,000. And we're holding that altitude with gamma equals 0, with a flight path angle gamma equals 0. On the bottom frame, you see again that the flight path angle cannot be maintained at 0 if the UAV cruises at 9,000 meters. Actually drops down from 0 all the way to minus 1.5 degrees. So here the answer is, well, the cruise ceiling of this UAV is 8,000 meters. So the students go through all these plots and determine the best gains and the performance of this UAV. Once that's all done, now the fun begins. Now we're going to test our UAV design on the computer, which is much cheaper than free flight testing. And even in a real hardware program, such a virtual flight testing should always be done. Matter of fact, it is always being done. The design is first tested extensively on the computer before the hardware is taken out to the test range. But here we are satisfied with virtual flight testing. And what I give the students is a test flight trajectory. You see it here in 3 dimensions: launch through 3 waypoints to the IP. On the right-hand side, you see that the launch is started at Long Lat and heading east at an altitude of 7,000 meters, and we launch it at Mach 0.64. So it first holds the altitude, and then after waypoint 1, it drops down, flies through waypoint 2, drops down further, flies through waypoint 3, and goes into the IP. So the students would use this trajectory to demonstrate to me and to the other teams how well their design performs. And they will show a plot like this here, which is now that same trajectory against time. And you see on the bottom here the 3 waypoints identified and the IP. Altitude is in red. See, after waypoint 1, it drops down from the original 7,000 meters down to 5,000 meters, cruises at 5,000, drops down to 2,000, and then goes through the IP. We're following the Mach number. Well, the launch is at 0.64, but we want to cruise at 0.7, which is pretty much obtained while it cruises at this 2,000 meter altitude. No, that's the 5,000 meter altitude. And of course also during the 2,000 meter altitude. We're looking at the dynamic pressure because that is so important for controllability of the whole flight vehicle, which looks very good. On the bottom, we see, particularly looking at the bank angle and then the angle of attack as the UAV makes the turns from one waypoint to the other. Well, this is a typical flight profile that would be used for the fly-off. So when that is all done, the students prepare a final report. They will summarize the requirements, their design in terms of layout, the aerodynamics, how they got them, what kind of turbojet, their control and the guidance selection. Then they would tell us something about their modeling and simulation attempt, and they would have to provide the source code with all the input files so we can check it out and then show the results of the final virtual flight test that validates the requirements. And finally, providing the briefing charts. So here we are, and the question is, what is the most important purpose of computer simulations? You have had time to think about this. Is it guiding and validating design, integrating components, verifying performance requirements, supporting test planning and analysis, very important in my opinion. Maybe training and practicing dangerous procedures, that would come in case of aircraft designs. Maybe just bragging rights. Well, I have a simulation and you don't. Or you may say all of the above. Okay, so the design is done, the virtual flight testing has been conducted, and now we're ready for a wrap up. Let's wrap it up now with a discussion of the benefits of computer-based prototyping, giving you access to my simulation and some additional resources that you may use to start your own projects. You may ask what students will learn from such a design course. Well, they'll learn how to apply multiple design tools, like for layout TurboCAD, for aerodynamic predictions, StatCom, for control design, MATLAB, and then how to integrate these components into an overall UAV, which is done by modeling the aerospace phenomena mathematically, and then building and using a computer simulation that represents this UAV design. Yes, in short, they will learn how to conduct virtual prototyping. Now, if you want to get my UAV simulation, you just send me an email and refer to the simulation name Cruise3_22. It is compatible with Microsoft Visual Studio, which you can download. If you are not working for industry, it's actually a free download. You can also download my plotting program from the AIAA website that I give here, which is compatible with the Windows operating systems. Or the other option you have is to use comma-separated variable option. So other resources that may help you with your own project, or if you develop a project for the students, it will help the students. This is here my graduate textbook published by AIAA, and AIAA also published 3 CDs of the 3 courses I taught at the University of Florida, an introductory course in C++, fundamentals of SIG-stuff simulations, and advanced SIG-stuff simulations. As part of my company, I published an undergraduate textbook, Introduction to Tensor Flight Dynamics, which is the parallel to my graduate textbook that I just showed you. And then a more advanced book of a 3-stage solid rocket booster being inserted into orbital conditions using the CADAC framework. I also created 4 workbooks about C++, tensor flight dynamics, missile and rocket simulations, and a more introductory workbook on flight dynamics. Now, if you want to take some online courses, you go to Udemy and take my course on flight dynamics with tensors, which is an introductory course, or take the course about C++ in aerospace simulations. You also can go to YouTube and take 2 seminars. The first seminar on Einstein is he actually affects flight dynamics, leading to the tensor formulation of flight dynamics. Or if you're interested in my CADAC framework, you can take here a seminar. Now it's time to say goodbye, and your takeaway of this aerospace design course is that the students learned how to do teamwork, computer skills, and how to apply many of the aerospace disciplines. They also got exposed to my CADAC framework with its UAV 5-staff simulation. So thank you very much to stay with me all the way to the end of this seminar.